Okay, so last time we have discussed that the reactions of reactions of singlet oxygen. Singlet oxygen plays an important role in organic photochemistry. Singlet oxygen is generated on irradiation of a methanolic solution of dye, methylene blue or rose bengal in the presence of oxygen atmosphere. So under irradiation, atmospheric oxygen is converted to the singlet oxygen, and singlet oxygen, we have also discussed that singlet oxygen uh, reacts with organic compound three different ways. First one is it undergoes in reaction, may also undergo 2 plus 2 photo addition, it also undergo 4 plus 2 cycloaddition reaction, and we have looked into different example. So we have also seen that the say for example, if we have anthracene, we have endoperoxide. So it is endoperoxide reaction. So anthracene, so this is a 9 10 9, this is 9 position, 9 10 9 10 diphenyl anthracene, 9 10 diphenyl 9 10 diphenyl anthracene. Under photolytic condition, oxygen generates singlet oxygen, and here this anthracene 4 plus 2 addition, 4 plus 2 addition with singlet oxygen to give endoperoxide. Right. So this diene, these two double bonds acts as 4, and then of course with the oxygen. So it is a, say for example, you have an oxygen, we have so it is adding across these two double bonds. So we get an endoperoxide like this, right? The two phenyl groups are already there. So we have this one. So this is the endoperoxide, is the product of reaction of anthracene with singlet oxygen. This endoperoxide on further photolysis undergo homolytic cleavage of this peroxide bond, homolytic cleavage of homolytic of peroxide bond to give an intermediate O dot pH, this O dot pH, and then of course there are two benzene rings. Now it has been observed that this O radical, oxy radical, adds to this double bond, and then this adds to this, and then gives rise to a product like this. So we have pH, we have pH, we have pH. So this is the and then this undergo further reaction to give different products, ring expansion product, and so on and so forth. So it's a very interesting reaction of 910 anthracene derivative. The 910 position, the oxygen adds in a 4 plus 2 manner to give rise to endoperoxide. This endoperoxide, Endoperoxide on further photolysis undergo homolytic cleavage of the peroxide bond to give a oxy radical, and then it can it adds to, there is no double bond here, it adds to this, and then this undergo further ring expansion product and so on and so forth. So another very interesting the transformation is observed from this particular endoperoxide. The not endoperoxide is peroxides. We have a this one, you have a peroxy linkage to cyclohexyl. The interesting remarkable phototransformation this undergoes. This undergoes H nu, the remarkable phototransformation. So this as we have seen last time, the peroxide undergo homolytic cleavage, and in the presence of light undergo homolytic cleavage to give oxy radical O dot O right. Now this opens up, the 6-membered ring opens up, formation of a O dot becomes carbonyl, and then this cyclohexyl ring opens up, same as here, this becomes carbonyl, this opens up. So we get a 6-membered ring, a carbonyl here, let's number this 1, 2, 3, 4, 5, 6. So at 1, so you have 1, 2, 3, 4, 5, 6. So at 6 carbon we have a radical, and then same as here. So there is a oxy, and then we have a carbonyl. So let's number this 1, 2, 3, 4, 5, and 6. So there is a, this is 1, there is a carbonyl here, 1, 2, 3, 4, 5, 2, 3, 4, 5, and 6, right? So this is a and then this once again combines radical coupling, is going to this how many so you have a 1, 2, 3, 1 okay, 1, 2, 3, 4, 5, 1, 2, 3. So we have a 2 carbonyl, we have a, and now there are CH210. You can see a very nice transformation. The 2 peroxy linkage is converted to 2 carbonyl as a part of the benzene ring, the cyclohexyl ring opens up, and this on further reaction H nu undergoes similar homolytic cleavage to homolytic cleavage. So let's write here homolytic cleavage of this. So we have a C double bond O radical, and we have a O radical, and then C double bond O, and then we have a CH2 10 times, right? And then this loses one, when this loses loses 1 molecule of CO2, then there is a loss of this, or it may also lose 2 molecules of minus 2H2, this also goes. So when it loses 1 and then combines, we end up with this CH2 10, and then if we both CH2 10. So it is just a carbocyclic system, and then this is a electron system. So this is a remarkable photoreaction which is observed in the case of this particular starting material. So people have designed interesting starting material, taken interesting starting material and see what is the product obtained, and then we can see that we have this leads to interesting product. So this is the regarding. Now the another class of reaction, photochemistry or oxirane. Photochemistry is a three-membered oxygen containing heterocycle. So if we have a system like this, tetraphenyl oxirane. So this under photolytic condition undergoes an opening like this to give an here C double bond O with the positive charge here, pH and pH. So this is an intermediate dipolar also dipolar is called a deuteronic intermediate. Intermediate is a SOI2 is a German word, and then this deuteronic intermediate has been exploited to can add in a with a dinophile, can add in a can act as a 3+2 cycloaddition. The 1 2 3 3 plus 2 cycloaddition with the dinophile, cycloaddition with dinophile such as DMAD, dimethyl acetylene dicarboxylate, CO2CH3. So this can add attack on this acetylene bond, and then so what we end up with a 5-membered ring. Right, we have a double bond here to dimethyl dicarboxylate, CO2CH3, and then we have 2 phenyl groups, pH. So this is a very important intermediate which is formed on photolysis of oxirane to generate a dipolar species which can be exploited to construct and a larger heterocyclic system. It has also been found that this intermediate on heating gives rise to on heating or under photolytic condition, it opens up to generate a carbene, pH plus ketone. So the is an opening like this to give a diphenyl carbonyl. So these two, and then again diphenyl carbene, which is generated as an intermediate during the photolysis of this oxirane, can be exploited to construct a cyclopropane ring, can add to a double bond, and to generate a three-member ring system. Construction of three-membered system. So this is a very interesting reaction which has been reported by German scientist, we'll call it Huygens, has done a lot of work on the aziridines. He has also done a three-membered nitrogen containing heterocycles, also undergoes in similar fashion to give a dipolar species, and this can be exploited to react with rhinophile to give a five-membered ring nitrogen containing heterocycle. So this is further going to the reaction of a three-membered ring. Of course, we are here a small ring system, photochemistry under the heading under the photochemistry of a small ring system, photochemistry of so if we have a diphenyl cyclopropane, and then so this diphenyl cyclopropane 1,2-diphenyl cyclopropane. Of course, it is a cis orientation. Under photolytic condition, it can undergo either via S1 excited state or if it is insensitized. If the direct photolysis going via S1 excited state, and sensitized photolysis may go by triplet excited state. It has been found that the triplet excited state leads to a diradical species, whereas the singlet excited state goes via the dipolar species, and then this will undergo coupling. Of course, when it is a ring is open up, there is a free rotation is possible, and it has been found to give pH a trans. So cis trans isomerization leading to cis trans isomerization of cyclopropane. Cis trans isomerization on sensitized photolysis of cyclopropane ring going via radical triplet excited state, which is in turn going via dipolar species. On the other hand, the reaction proceeding via singlet excited state is a dipolar species, proceeds via dipolar species, and it has been trapped by polar solvents, So when it has been found that when it is treated with RNH2, it gives rise to, of course, there is an abstraction of a NHR, and then this can abstract a proton from this, of course, and then deprotonation. So this is a very you can see that the cyclopropane ring shows two different photochemistry under direct photolysis going via a singlet excited state leading to a dipolar species which has been trapped by polar solvents. On the other hand, sensitized photolysis of this 1,2-diphenyl cyclopropane proceeds via diradical species, and then which may lead to cisterns isomerization. The photochemistry of sulfones has also been reported. Photochemistry of sulfones was the extrusion of SO2 has been reported. And then if we have a system like this, SO2, and then of course we have a cis orientation H nu, and this C6H6 is the sensitizer going via 1, 2, 3, 4, 5 leading to 4 plus 1. So it is just a extrusion of SO2 leads to leads to fusion of SO2. So it has been reported to give this plus SO2, and then this is a major product. So on the other hand, if we have a trans so also undergo under similar condition, benzene as a solvent, 5 extrusion of this takes place. Right, to give 5 going to 4 plus 1, I mean extrusion. So here the major this is the major product, and here is the major product. This is the major product. So you can see the stereochemistry. This is a stereoselective. The reaction is stereo leading to inversion leads to inversion in stereochemistry. So you have a cis, it goes to trans, and trans going to cis. Stereochemistry. Right. So we go further, and we can see a very the cyclobutene. We have a cyclobutene undergoes causes retrocycloaddition reaction. Retrocycloaddition means the 4 going to 2 plus 2. So and quite few examples of this type are available. So one of the example here is the 6-member ring, a 4-member ring, another 6-member ring, and this is we have a cis. This in the presence of light, H nu, this rotatory, this we going to 4, this going to 2 plus 2 system, and then you can see here this is cyclobutene derivative, cyclobutene, and then you can see here. So you have a generation of a triple bond. You have a generation of a triple bond. So and then a 1, 2, a triple, and then of course we have a generation of a double bond here. Right. So we can see it is a very good reaction, and plus it also gives another product where the this becomes opening is opens up here. The ring opens up. This is a ring is intact, but there is also possibility that this rings opens up. Rings opens up in this fashion. Sorry. This opens up. So both this is a both the rings are in are attached through a single bond. So we get two products here. We have and with of course two double bonds here as well as here. So this type of reactions have been reported in the case of cyclobutene, the retro cycloaddition reactions, and if we have a trans ring junction, then there is another. If we have a cis ring junction, if you have a trans ring junction. So this under photolysis, this rotatory and 4 going to 2 plus 2, and it opens up. Of course, shows the double bond is retained. So you have a triple bond, and then you have a trans. You have okay. So of course, okay. So we just got change. So you can see this plus it also gets one more product. So let's write. So this one, and then we get a plus it also gets another product. As we can see, two products are obtained. H, then we have a right. So retro cycloaddition reactions. So these are two examples of retro cycloadditions of cyclobutene. The cis ring junction undergo ring opening to give a ene one double bond and a triple bond, and also the trans ring junction. This stereochemistry is retained, and then